Today we've got a video about the Fibonacci numbers, and in fact we're going to prove a result that is very easy to state, but it's a little bit tricky to prove. And that is, we're going to classify all of the perfect square Fibonacci numbers. So in other words, when is the Fibonacci number a perfect square? And this is based off of this nice paper by John Cohn from the Fibonacci Quarterly from 1964. So in order to do this, we'll not only need the Fibonacci numbers, but also the negative versions of the Fibonacci numbers, as well as the Lucas numbers. So let's recall the Fibonacci numbers have seeds 0 and 1, and then our recursion takes over. So the n plus second term is the sum of the n plus first and the nth. And then we can define the negative Fibonacci number f sub minus n as minus 1 to the n plus 1 f sub n. And then the Lucas numbers have the same recursion, except now the seeds are 2 and 1, and the negative nth Lucas number is minus 1 to the n L sub n. Okay, so we're going to use a couple of lemmas or smaller results to get to our final result. The first one is this three-parter. So let's focus on one part at a time. So part number 1 says that L sub n is congruent to 0 mod 3 if and only if n is congruent to 2 mod 4. So what does that really mean? Well, being congruent to 0 mod 3 means that you are divisible by 3. So these are all of the Lucas numbers that are multiples of 3. And then being congruent to 2 mod 4 means that when you divide something by 4, you get a remainder of 2. Okay, so how are we going to start this? Well, we're going to start it by just doing a couple of starting examples. We're going to need 4 in total because we're working mod 4 with this n. And then it'll follow very, very quickly. So let's notice that L sub 0 is 2 by, our seed over here. L sub 1 is 1, again by our other seed. That makes L sub 2 equal to, well, it's the sum of the previous 2. So the sum of the previous 2 is 3. And then L sub 3, that'll be the sum of the previous 2, which is 4. And now let's notice that this one in the middle, L sub 2, is the only one that's congruent to 0 mod 3. Furthermore, the index here is the only index that's congruent to 2 mod 4. Okay. And now what we'll do is just build a recursion, well, a recursion for our purposes out of the given recursion that will finish this off. Okay, so let's look at it. So we'll start with L sub n plus 4, and we'll note that we can write that as L sub n plus 3 plus L sub n plus 2. And then from there, we can apply the recursion to this L sub n plus 3, as well as this L sub n plus 2. So that'll be L sub n plus 2, we'll have n plus 1, L sub n plus 1, and then L sub n. So we got 2 copies of that L sub n plus 1. Okay, and then we're going to apply the recursion one more time to this L sub n plus 2. So that'll give us another L sub n plus 1. We'll combine it with those two to have 3 L sub n plus 1. And then it'll give us another L sub n, so we'll have 2 L sub n. But let's note that that is congruent to 2 L sub n modulo 3. And that's because we've got this 3 right here. This thing right here that I'm underlining in red is most definitely a multiple of 3. But now we just apply this rule over and over and over again. And so in order to move 4 ahead, all we have to do is multiply by 2, well, mod 3. So that means to move 4 ahead here, we multiply by 2 mod 3. But 2 times 2 mod 3 is 1, so that tells us that L sub 4 is congruent to 1 modulo 3. And then we continue this on. To move this 4 ahead, well, we'll multiply by 2 mod 3. So that'll give us, let's see, L sub 5 is 2 modulo 3. But then again, to move this thing 4 ahead, we'll multiply by 2, but multiplying 0 by 2 just gives us 0. So here we get L sub 6 is 0 modulo 3. And then again, to move this ahead, we'll do something similar. I'll leave that calculation for you. And so this allows us to push forward, and notice that we'll only get a multiple of 3 for L sub 2, L sub 6, the next one will be L sub 10, then L sub 14, so on and so forth. But those are all of the numbers that are congruent to 2 mod 4. And although this was presented kind of somewhat casually, it could be rewritten carefully to have a proper if and only if statement. Okay, let's move on to the second result. Okay, so our second result says that if 2 divides n and 3 does not divide n, then L sub n is congruent to 3 mod 4. So this is a little bit trickier. So let's maybe start with our hypothesis. So 2 divides n and 3 does not divide n. But the fact that we're talking about dividing by 2 and 3 means we should probably be working with numbers of the form 6k plus something. And so if we have this set up, 2 divides n, but 3 does not divide n, that actually kind of, somewhat logically splits into 2 cases. The first of which is n is equal to 6k plus 2. The other one is n is equal to 6k plus 4. But that's all we get. And then from here, we'll look at these one case at a time. So let's say this is our first case when n is 6k plus 2, and I'll likely leave the second case as a homework exercise. Okay, so we've got L sub n in this case is the same thing as L sub 6k plus 2. But now let's apply the recursion to that. That'll give us L sub 6k plus 1 plus L sub 6k. But now we're going to apply the recursion to both of those terms. I think you can see a pattern. We apply the recursion to either all of the terms that are present or some of them to get some sort of structure into our object. Okay, so applying it to this first term, we'll get L sub 6k plus L sub 6k minus 1. Applying it to this second one gives us L sub 6k minus 1 plus L sub 6k minus 2. And then next up, we'll apply it to this one only, which I've boxed in brown. And that'll give us another L sub 6k minus 2 and another L sub 6k minus 1, pretty similar to our last calculation. So we'll have this is 3 L sub 6k minus 1 plus 2 L sub 6k minus 2. And now here comes a tricky part. We're going to apply the recursion again to this L sub 6k minus 1 and apply it to one of these L sub 6k minus 2's. So let's see where that leaves us. We have 3 L 6k minus 2 plus L 6k minus 3 plus L 6k minus 2, because we're leaving one as is, and then applying the recursion to the other one, we'll get L 6k minus 3 plus L 6k minus 4. Well, since we're working with a number of the form 6k plus 2, we need to get down to the previous number of the form 6k plus 2. But the previous number of the form 6k plus 2 is 6k minus 4. That's because we can envision this as L sub 6 times k minus 1 plus 2. Oh, but that means we've gone deep enough. So what we'll do is combine all of the like terms. We have a couple, and then we'll see what we have with respect to this L sub 6k minus 4 left over. Okay, so check it out. We've got a 6k minus 2 term here, a 6k minus 2 term here. This one's attached to a 3. That gives us 4 L sub 6k minus 2. We've got something similar happening with the L sub 6k minus 3. So we've got 4 L 6k minus 3. And then finally this single L sub 6k minus 4. Okay, great. But now our final goal is to work mod 4. So reducing this mod 4, we'll get rid of these two terms because they have, well, 4 multiplied into them. So this is all congruent to L sub 6k minus 4 modulo 4. Okay, great. And so now where would you go from here? Well, you would do essentially the same thing that we did in the previous case. You would look at the first 4 Fibonacci numbers and reduce them mod 4. Well, we had that on the previous board, so I'll let you check that. And then applying this recursion allows us to bootstrap forward, thus generating this result. And then this other case is really similar, almost exactly the same. So I'll let you do that on your own, and also I'll let you do this number 3 on your own. You can prove this by induction if you'd like. Okay, so now let's move on to our next result. Okay, so now we're gonna classify all of the perfect square Lucas numbers, and then we'll use that to do the same thing for Fibonacci numbers. So what we have is that if Ln is a perfect square, so if it's equal to x squared, then n is equal to 1 or n is equal to 3. In other words, the only square Lucas numbers are L1, which is 1, or L3, which is 4. Okay, so how does this proof go? Well, we're going to break it into 2 cases based off the index being even or odd. So the first case will be the index is even. So we've got n is equal to 2m. And now that means we have L sub n is equal to L sub 2m. But we had a result about that. That was the portion of the lemma we didn't prove. And that means we can write this as L sub m squared and then minus 1 to the m times 2. Okay, but now let's notice if L sub 2m equals x squared, well, that's the same thing as L sub n being equal to x squared, then we have a solution to the following equation. X squared equals y squared plus minus 2. And so this y is just L sub m in this case, and then we get a plus sign if, let's see, m is odd, and we get a minus sign if m is even. But in fact, we won't really care about if this is a plus minus 2 because we're going to work mod 4. Okay, so let's maybe point that out here. So working mod 4, that means we've got a solution to the following congruence. We have x squared is congruent to y squared plus 2 modulo 4. Okay, great. And so now we're going to break this into 2 subcases. So if y is even, in other words, we can write it as 2 times z. That means that y squared is equal to 4 times z squared. But that's a multiple of 4. So when we reduce it mod 4, that kind of disappears, and we're left with x squared is congruent to 2 modulo 4. Oh, but a really important fact is that 2 is not a perfect square mod 4. I think we use that on the channel from time to time. That's a pretty easy thing to show. So that gives us a contradiction here, leaving us with the only other case, which is y is odd. So if we have y is equal to 2z plus 1, then that means that y squared is 4z squared plus 4z plus 1, just like multiplying it out. But notice we've got 2 multiples of 4 here that will disappear when we reduce mod 4. So now plugging that into our congruence right here, we'll have a 1 which combines with this 2, and we have x squared is congruent to 3 modulo 4. But again, 3 is not a perfect square mod 4. I think maybe you can guess by this little calculation right here that the only perfect squares mod 4 are 0 and 1. We can see that because if we reduce this mod 4, we get 0 mod 4. And if we reduce this mod 4, we get 1 mod 4. And that really covers all of the cases because here we started with an even and here we started with an odd. But that's kind of beside the point. What we ended up with here is a contradiction, which means we don't have any square Lucas numbers if the index is even. Now let's move on. Now the other case will be the case when n is odd, and that actually splits into 2 subcases. Because working mod 4 again, there are two types of odd numbers, those of the form 4m plus 1 and those of the form 4m plus 3. Now, when you work through this, you'll want to work through the case when m is bigger than 1, and then just check the case when m is equal to 0 and m is equal to 1 kind of on their own. Then, furthermore, I'm just going to do this blue boxed case up here when we have 4m plus 1. I'll leave this as a homework exercise. It's pretty similar. But notice the m equals 0 case here gives us our n equals 1 set up here, as well as the m equals 0 case in this one we're skipping gives us the L sub 3 equal 4 setup. Okay, so let's move on with this. Okay, so if n is equal to 4m plus 1, that means we can write n as 4, and then we'll write m a certain way. We'll write it as 3 to the r times k, and then we'll have a plus 1. So just to reiterate what we did right here, we factored out all possible multiples of 3 from m. So I guess it's important to note here that 3 does not divide k. We're factoring out all of the 3-ness from our number m. And so that could be no 3-ness at all. We could have r is equal to 0, but that's okay. And now for the purposes of time here, I'm gonna leave another homework exercise. So there's kind of a lot of homework exercises in this video, but I think that's okay. So, and that would be that in this setup, we have L sub n is in fact congruent to negative L sub 1 modulo L sub 2k. But L sub 1 is simply equal to 1, so this is in fact congruent to negative 1 mod L sub 2k. Okay, great. And now we're ready for the final argument of this case. So let's say we have if L sub n is equal to x squared, then what do we have? That means that x squared is congruent to negative 1 modulo L sub 2k by this result right here, which was the homework exercise. Then let's also recall from a portion of our lemma, we know the following fact, and that is that L sub 2k is in fact congruent to 3 modulo 4. And now we're going to apply a fairly general rule about perfect squares. And that is negative 1 is not a perfect square mod 4a plus 3 for all a bigger than or equal to 0. So this is something you would learn in like an elementary number theory class. But that leads us to a contradiction, because here we have x squared is congruent to negative 1 mod. Well, L sub 2k is most definitely of the form 4a plus 3 by this result right here, which followed from that lemma. Okay, so anyway, what we have here is that contradiction. So that contradicted the fact that we could get a perfect square Lucas number of the form 4m plus 1, except for the case when m is equal to 0, which is one that we can already check on its own. Notice we really needed m to be bigger than 1 here, so we were able to factor this 4 out. In the case when m is equal to 0, we can't factor this 4 out. Okay, so now I'm going to present another theorem which we won't prove, but we will use to prove our final result about square Fibonacci numbers. Okay, before we look at our main result, here's that kind of bonus theorem. Go ahead and read the paper. Recall, you can find it here if you want to see the proof. And that is that L sub n equals 2 times a perfect square if and only if n is equal to negative 6, 0, or 6. Okay, now for our main result. That says the only square Fibonacci numbers are f sub 0, which is 0 squared, f sub 1, which is 1 squared, and f sub 12, which is 12 squared. Okay, so our proof will be broken down to our proof will break down into a couple of cases. The first is when n is congruent to 1 mod 4, but n is bigger than 1. Again, when n is equal to 0 or 1, you can check that on its own. Okay, so that means we can write n as follows. So n is equal to 4 times 3 to the r times k plus 1. And so that's kind of in line with what we did in our previous result. And from here, we're gonna apply another kind of like obscure congruence between Fibonacci numbers and Lucas numbers. And that is, in this case, f sub n is in fact congruent to -1 mod L sub k, where k is this number right here. Okay, but now let's take it home. So if f sub n is equal to x squared in this case, then that means that x squared is congruent to -1 modulo L sub k. But now in this setup, using the method of proof that we saw in the Lucas numbers, we know that L sub k is congruent to 3 modulo 4. But now putting these two things together, just like we did before, there are no perfect squares of the form 4a plus 3, so that brings us to a contradiction. Okay, and then actually the second case is so similar that we can just squeeze it into the bottom right here. And the second case is for the other types of odd numbers. And so in other words, n is congruent to 3 modulo 4. And again, n is bigger than 1 in this case. But let's notice if n is congruent to 3 mod 4, that means -n is congruent to 1 mod 4. That's because 3 is congruent to -1 mod 4. Okay, but now let's look at f sub minus n, which in this case is the same thing as f sub n. Because of this rule right here, we have an even exponent. But now f sub minus n cannot be a perfect square by kind of a bootstrapping of this result right here towards negative numbers. But that means that f sub n cannot be a perfect square. So that wraps up all of the odd numbers. Okay, so now let's look at the even case. Okay, so now for our third case. And this is the case when we've got an even index. So I'll write that index as 2 times m. And so we want to suppose that f sub 2 times m is equal to x squared, and essentially show that the only possible value for m is 6, giving us this f sub 12 case. Okay, so now let's maybe reverse this equation and note we have x squared is equal to f sub 2m. And now we're going to use a Fibonacci-Lucas number like relationship or identity to write this as f sub m times L sub m. And we're going to use another result based on the greatest common divisor of these two numbers. Well, the Fibonacci number and the Lucas number. So we have the GCD of f sub m and L sub m is equal to 1 if 3 does not divide m, but the GCD of f sub m and L sub m is equal to 2 if 3 does divide m. And that's going to break us into two subcases. So I'll number this first one 1 and this second one 2. And so let's look at this first subcase. Okay, so if 3 does not divide m, well, this GCD is 1. But if this GCD is 1 and we're multiplying these two things to get a perfect square, that means these both have to be a perfect square. So in other words, we have a perfect square Lucas number, which is going to be y squared. It's just the portion of x squared that is not taken up by f sub m. Okay, but what does that mean? Well, that means that m can only have two values. We proved that previously. And so m can only be equal to 1 or m is equal to 3. Those are the only two possibilities. But notice this case when m is equal to 3 is excluded because we're in case 1 when 3 does not divide m. So we don't get anything right there. But if m is equal to 1, then that means that we're looking at f sub 2, but notice that f sub 2 is also equal to 1. Well, I guess that's a perfect square, but it's the same perfect square as f sub 1, so I kind of left that out there. Maybe comment or edit your comment if you corrected me already on that. Okay, so now let's move on to our second case. And our second case, we'll use this theorem over here. Okay, and that will be the GCD of FM and LM equals 2. Okay, but that means they're both divisible by 2. Oh, but that means we should be able to write L sub M as 2 times y squared. Oh, but we've got a result for that. It's over here. So that means we have M is equal to -6, M is equal to 0, or M is equal to 6. So notice if M is equal to 0, that gives us F sub 0 is 0. Well, we already have that. If M is equal to 6, that gives us F sub 12, which you can check by the recursion or by building up the Fibonacci numbers, that F sub 12 is 144, which is in fact 12 squared. And then you've also got this case when M is equal to -6, but that most definitely does not work because by this rule over here, we have F sub -12 is equal to -144, which is a negative number, so it cannot be a perfect square. Okay, so through all this, we came up with our final result, that the only square Fibonacci numbers are these, well, 3 or 4, depending on how you count them. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.